What's up, everybody? Welcome to Earth Science. Let's talk waves and shoreline processes and get into thinking about why certain shorelines have certain shapes. So, if you've ever sat and watched waves coming at you, what you're seeing coming at you is like really energy. It's not actual physical water working its way across the surface. I mean, we're all close to Lake Ontario here, right? So, if you are watching waves, let's say there's the bottom of Lake Ontario, there's the beach, there's you, right? And we'll add some water in blue. When you watch these waves coming at you, boy, that's terrible. It's not this actual bit of water coming forward. Then you would need some kind of like sheer surface that the wave would slide across. It would look really bizarre. What you're seeing is energy that's been put into the water, usually by winds, approaching and like knocking into the next one, knocking into the next one, knocking into the next one. Um, Let me try to make the wave a little bit bigger. So when we have a wave, what really happens is that there's energy going in these orbitals. So if you could focus in on one molecule of water as a wave passes by, it's going to be going like this around in these little loops. And below that, there's going to be a smaller one. And below that, there's going to be a smaller one. And below that, there's going to be a smaller one, down to a depth, which depends on the wavelength, how long the waves are. But at some point, right, the water over here is going to be deeper than that. But at some point, these orbitals start to interact with the ground. And that's where you start to see waves breaking. What also happens is that as they drag on the ground, they can refract, they can bend. We talked about light waves refracting or bending. This is kind of the same idea. It's a wave bending. So the waves will bend their way so that by the time they hit the shoreline, it's roughly parallel. The surface going across the wave is parallel with the beach that it's crashing on. So when you have kind of a curvy bay like this, you end up refracting and concentrating energy in some areas. So when you concentrate it, that's going to be high energy. And what really comes down to here is going back to the good old reference tables, which I'm going to have to pull up here. Remember this guy? This is the same deal. Yes, we talked about this when we were doing rivers, but the larger story was that if the water speeds up, it can carry larger and larger particles, what we call erosion. And if it slows down, it can't carry them anymore, so it drops them off, what we call deposition. So apply that same idea. I know it's not like constricted in a river, but it can still take place. If all the energy is getting concentrated, these areas that jut out are going to get beat up on. It's going to be a high energy environment, so sediment is going to be taken away from there. And where these spread out, it's going to be a lower energy environment. And that's why we're going to see deposition there. So does this hold up in real life? A good example of this is down in Rhode Island. There we go. On the beaches in the south end of Newport Island, as this thing very slowly loads. This is the headland right here. It'll come into focus in a moment. And then these are where the waves get dispersed out. So energy gets concentrated towards these. And as a result, sorry, is it taking so long to focus? Network is grumpy today. As a result, we see all rock here. This is like a high energy, constantly being beat up by the waves environment that I really wish would focus better. Whereas over here, where it gets all spread out, is going to be the lower energy environment, which is why we have deposition there. So here's some nice beaches. And again, the rocky headland. There we go. It focused in. So rock, 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 rock. All right. So I'm not making it up. Right. So what else can happen? And you can notice this on the beaches here at Lake Ontario is that with the direction of the prevailing winds and how the waves might come in at a little bit of an angle, you end up getting a drift along the shore, parallel to shore, which we'll call a longshore current, and the sediment in it we'd call a longshore drift. And what that does is gives you certain features that run parallel to the shore. So if you've gone to these beaches locally and had sandbars, then you've seen it. Or if you've gone to the ones that are like near Sandy Pond here, this is exactly how this happens. Water comes up the shoreline. The current comes up the shoreline here from the south heading north. and deposits sediment as it goes. So these sand dunes, like this, really should be the shape of the lakeshore, but this longshore drift has deposited this long pile of sand dunes, a spit it's called, or a barrier bar if it completely encases the whole thing, that now makes that shoreline nice and smooth. And if you've goofed around on the beaches here and like had sandbars where you go in and it gets shallow, and then all of a sudden, well, you go in initially, it gets deeper, and then all of a sudden it gets shallower because you're on a sandbar. Those are the moving bits of sand along with this longshore currents that work their way this way upshore slowly over the course of years. And there's examples of this all along the beach. Right? Longshore current deposited that spit. Now they put in some barriers here. We'll talk about those in a few minutes. Longshore current covers up right along that beach. These things are all over this edge of the lake. We'll go to my neck of the woods. And this one actually, for years, this one was completely right across. But I'm sorry, this is loading so slow. But with the high water we had in the last couple of years, it's now eroded itself right down. But it will be rebuilt again. There we go. So that was a complete bar right there. You could walk right across it. This is Little Sodas Bay. This is over towards Fairhaven. Now those high water years blew that thing right out. And I'd suspect through the years it'll build its way back in. All examples of longshore drift. So when you might have experienced it is if you've gone to that beach and played, maybe you've noticed that every once in a while you end up like a little further to the north and you say, wait, where's the family? And then you see they're over here and you got to like work your way back. It's not necessarily a current that you would feel, but if you sit there and each wave bumps you over like a centimeter as you're goofing around in the water, eventually you end up following that longshore current downstream. So I don't know. That's most of it. Is there anything else in the notes we want to get? I think we're good. I mean, I'm not going to have you write anything necessarily because you've already got it all on there. Let's talk about what we do. And then these two questions are from the quiz you're going to try when you're done with this. What we humans try to do sometimes to slow this down is we build these groins, which is where you build a solid rock wall going out to interrupt the longshore drift. And it's a clever idea using that reference table because we say, okay, if we can slow down the currents, that will create deposition. And it does. So you end up getting a thicker beach on the side where the longshore current is coming from. But what happens is that water then comes whipping around the edge here, and it actually does more erosion over on this side. So if you're not careful with the planning and control of it, you end up being in a worse position where, yes, you made the beach thicker and larger here, but it's smaller and thinner here, possibly to a point of being dangerous. Selkirk has a small one, and you can't really notice a ton on it. A little bit, like right through here. This would be the side where the current is coming from, working its way up to the north. So there's a little bit more sand build up here. And when the water comes around, it speeds up. So it looks like sand is gone on this side, carried up towards Sandy Island Beach up there. There's a great example up in Chicago. Why don't I press pause to find it so that the loading doesn't take you forever? All right. Mission accomplished. Here it is. So those are built out into the water to slow down the longshore current. Now you should be able to tell me if you're getting this down, where is this current coming from? If we see buildup on this side and then erosion on this side, where's it coming from? The answer would be that it's coming down from the north. So these groins, will slow down the water and have sand deposit on the inside, but then it accelerates and speeds up on the far side and causes more erosion. So there's a really perfect example of how that works with longshore currents. All right. So yeah, this is going to be like the quiz isn't bad. So you'll really have to do that on this one. That's what this question will be, is which direction is the current going, knowing that the deposition's happening there. And same idea here. If this is kind of like all the processes. You got the headlands, the mainland being eroded and creating sediment, that sediment being transported, erosion, I should say weathered. It weathers out of the out of the pre-existing rock, right? The erosion is the transportation of that sediment. And then where would it get deposited? Well, it comes all along this barrier beach that separates out the lagoon. Or if we build a groin, where would it happen relative to that? All right. If you want to say, what are my couple of big points just to get out of here? Things like barrier islands, sandbars, they're all deposited by waves. There's like very repetitive questions in this classwork that are pretty much just like at least 5 of the 10 are like that idea. All right. Sound good, everybody? Take care. Hope that goes well. And we'll talk to you soon.